Okay, so let's pick these lots and assign these. It's like a birthday party, right? I'm sure every one of you has picked lots and had a treasure hunt. Okay, group one. Let's see, Chaitanya, Sudipta, and Rahul. So one of you can come and pick a lot. Yeah. Both of you want the honors. Fine. Pick one. What does it say? Electroweak precision. Okay, very good. Who's number two? Kirana, Kanishka, and Patsarathi. You are Kirana. Okay, pick one. Yeah. I know, doesn't matter. So it's only two of you. What can I do? Low energy, high precision. Okay. Durba is here. Durba, Devendra, and Indrayod. Some of these guys never come to class. Doesn't matter. B physics. Very good. Number 4, Leonard. Then AAGB. Any one of you is fine. No Abhishek today. This is already somebody. Yeah, that's why he's disappeared. G minus 2 for the muon. Okay. You can keep it. Yeah, and after I'm gone, you can keep it as a memento of all the love and respect you had for me. Okay. Neha, Aman, and Nikshay, you all know each other? Well, now you had better know. I guess so. And this is Neha, and that's Nikshay. Neutrinos. Very good. Yeah. So that leaves Anirudhya, Hamsini, and Shirish. Yeah. So that whatever is left. Higgs. Great. Okay, folks. So where is Mr. Kundu? I was hoping that he would come and take the class today, but he's not here. Okay. So what were we doing? I've even forgotten what we were doing. We did this E plus E minus to mu plus mu minus, no? We did this in some detail, if you remember. We had done all the Z boson and all. That was already probably the previous class. Then, I don't know. Maybe we don't. Okay. Yeah. Show me. If you have already done the notebook, you do a demo. If there's nobody else, about 3 or 4 people gave likes to that. So which one of you wants to give a demo? Yeah. Kundu's on his way. We have to wait for him. In the meantime, you show me what's the difficulty. Yeah. You can open a Teams page and show me. We are going to do all this very interactively. Otherwise, it's very boring for me. So you got a Teams page? Yeah. Okay, but it's going to come nevertheless. Okay. So let's see what you people have accomplished. That's the key thing. Otherwise, I can keep on talking till day's end, and there's no point to that. Very warm in here. Why is it so awful already? It's only January. So this group is called Standard Model. Okay. Let's go here. Let's take a picture. Ah, the man is here. Okay, good. So you have to give us a demo. You should have been here 5 minutes early instead of late. What, you have some other class in some other building? Overslept. Why? Why? That's why I never use the official version. I use only pirated versions. Hmm? Oh, well, I have to be taken away in handcuffs. Now, Trump will send his immigration people and deport me. But he can't deport me because I'm already home. Whatever you like, I mean, as I said, I can keep on talking till day's end. The point is, we must also assess how much you people have learnt, right? So we have already had 8 hours, 8 times 1.5 hours, which is roughly 30% of the course. So this is a good time for us to pause and see how much people have grasped and what difficulties you have, so on and so forth, right? And as you know, this is supposed to be a research level course. It's not about learning the alphabet and so on. So it's supposed to assist people in their research. That's the whole point of this course. Okay, so you're going to start now. Okay, you have something to share? Has he opened a Teams page? Oh, I didn't approve you. I don't know, there's something wrong. I have tried to approve, but it doesn't approve. Maybe it doesn't like you. That's all I can say. Teams, huh? Let me see. See, it doesn't show anything here. You will find notifications. Okay, activity. Let's see. View all activity. It shows everything is there. What can I say? I'll try again from my laptop later. Okay. Can anybody access it? Everybody except poor Nikshay. Nobody, he is not in a position to access. Yes, you can. There's a feedback. You can mute me. Yeah. You're not able to get in? But you said that I had not approved you. Hmm? Yeah. You can come and share with me. Otherwise, I will not be able to see it. I think we need to get a chair or two. Come on. Get a chair from the next room. Okay. Okay. So, yeah, tell us what you have. Hmm. Yeah, you. Let's have a look. And did you compare it with? Did you compare it with any published result? Okay. Oh, okay. So that must be some typo in his book. But the rest of the functional form is fine. Okay, let's have a look at the answer. You scroll down, let us see. For m squared. So, okay. So you have only the square of the matrix element, but you don't have the phase space factor. So you don't have the cross section. Doesn't matter. I'm just asking you. So let's start at the top and you explain to us what is the program. What are the various lines and what do they show? Start at the top. You do all this later, right? Let's follow him now. Yeah, yeah. No, no, say that again. Yeah, yeah. I see. Okay. Yeah. Why is the t squared appearing below? No, no, that's okay. No, 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 no. It's correct. So t is now the propagator, right? The propagator factor, the q squared, is t, and then you square it to get in the square of the, and because it's a t channel scattering, so that's why we are calling it t. Okay. Okay, then. Yeah, you explain all the terms, because not everybody here has learned fine calc. So explain what are all the commands that you have over here.
This spinner U bar constructs a spinner U bar, the electron, the bar of the electron function, the electron spinner, with momentum eq and mass n. N here is the mass of the electron.
Very good.
Ga is gamma matrix, so gamma matrix is index.
Okay.
Spinner U analogous to bar, spinner U bar without the bar.
Yeah.
With momentum e1 and mass of the electron.
Okay.
This is the first line. This whole thing is the first line.
See, also in the syntax, the dot is very important. Okay. So every one of these things has a meaning in fine calc. If you use the dot, it means that if you have spinors, matrices, etc., multiplication in Mathematica, matrix multiplication needs a dot. Okay. So every symbol that appears over here, every ASCII character that appears here has some meaning in the syntax. Okay. Yeah. Now spinner, U bar and all are inbuilt commands of fine calc. They are not commands of Mathematica, but they are of fine calc as far as I know. Okay. Now GA is also defined by fine calc. Okay. Okay. So the very first parenthesis that you have, it represents the electronic current. Okay. So it's the electronic current over here with one spinner for the incoming particle, one for the outgoing particle. The outgoing particle is a U bar, the incoming particle is a U. Okay. So these are the things. If this had been a positron, then it would have been a spinner V bar and a spinner V. Okay. So the inbuilt calculus of fine calc takes into account every one of these. Every symbol has a meaning. Spinner U is for the electron, spinner V is for the positron. Okay. U bar is, of course, U bar, which is U dagger with a gamma naught, is a bar, right? In the Dirac calculus, you know that a U bar is a U dagger multiplied by a gamma naught is already taken care of. So every single ASCII character here represents for you the Dirac algebra. Okay, it's all inbuilt. Okay. So he closes the parenthesis over there, and then there's no dot as far as I can see. There's no dot. Then another one is opening, and that is for the muon, where muon. Yeah, exactly the same. A muon is exactly like the proton, like the electron, except that its mass is different. So you can use the same spinner U bar for, except that you change the mass from Me to Mu. So it understands that it is a different particle. It doesn't know that it's a muon per se, but it knows that it's a different particle for sure. And what else does it know? Very good. Yeah.
That it calculates for us n times n star.
Yes. Yeah. Yeah. Yes.
So this is the same expression as above.
Excellent. So that's the first term, m squared. After m squared comes, you have to take the fermion spin sum. Why is that? Because you want to get rid of the spinners. and replace the spinors by momenta, p slashes and all so on, and this comes from the completeness properties of the spin sum. Okay, so the u bars are the different spins that you have when you take the fermion spin sum. The combination of a u bar and a u, if you sum over the spins, will produce the momentum sitting over there plus a mass. Okay, so that is what it does over here, and it produces a p slash for each one of them. That is why you see gamma dot p1, gamma dot p2, gamma dot p3, gamma dot p4. Okay, so that's the reason why you see this. Now let me ask you a question. Supposing the scattering was not because of the photon but was because of the z. This is also allowed by the theory. What would be the corresponding change that you would have to make? Oh, you've done that. Okay. Okay, so let's go on to this line and let's see what happens. Then he has something called Dirac. Why? So what is the Dirac simplify doing? See, if you go exactly, yeah. So Dirac simplify is another new command of the most recent versions of fine calc. Okay, so that is why it does Dirac simplify, and then it produces for you an answer that involves only scalar products of the momenta as well as the masses. Okay, so this is already a beautiful answer for us, which involves only scalar products of the momenta. So if it is scalar products of the momenta, this means that it's already in a Lorentz covariant form. So this is very nice. Once it's in a Lorentz covariant form, what are the things that you can do in the Lorentz covariant expression? What are the things that you can do? You can replace things like p1 dot p2 etc. by s and masses of the particles. If it is p1 dot p3, then you can replace it by t and masses of the particles. If it is p1 dot p4, what can you do? U and masses of the particles. Okay, in the center of mass frame. Now remember that although st and u, right, this is in the center, this doesn't matter, these are relativistic invariants. So this st and u are st and u irrespective of which frame you're in. But later if you go to the center of mass frame, there you identify s to be square of the center of mass energy, and you can replace t and u in terms of cosine theta, which is the scattering angle in the center of mass frame, if that is what you want. If you want the answer in the center of mass frame, then you can make the corresponding replacement in the center of mass frame. Okay, but you haven't done that. You could do that. You could use all kinds of commands to replace Mandelstam variables by cosine theta. Yeah, that I see. By using set Mandelstam is another nice command of fine calc, which has again a syntax. You have to know what the syntax is. So
the names of the variables you want to store st and u in. Then you name the momenta. Then you name all the four masses of the process, masses of the asymptotic particles of the process.
In the same order. Please remember, if you call them p1, p2, p3, p4, then the masses had better be the mass of the first particle, second particle, third particle, fourth particle. Okay. If you mess this up, then you'll get garbage, obviously, right? So the syntax is very important as far as definitions of these things are concerned. Okay. What is strict Mandelstam?
Strict Mandelstam is it simplifies your expression. The earlier expression that you get out of st and u. See, this is the expression I want to simplify.
Okay, fine, yeah. Okay.
It produces the shortest possible expression there is by taking one of st and u in favor of mass.
Very good. Okay. Now here, this is one way of looking at this. The other way of looking at this is to be able to replace st and u in terms of sine theta and cosine theta, so that you actually get an answer that looks like a physical scattering amplitude. Whenever you think of a scattering amplitude, you want it to be a function of cosine theta, right? Scattering amplitude. The st and u, okay, fine, looks very nice. So there is a command. Has any of you done this replacement over here? Yeah. No, there are these relations. No? Just give me those notes. Yeah. See here, this E mu scattering. Yeah, so you can give a replace command, and also there is you have to figure out what is, or you have to replace t by yeah, forward slash dot. You can replace t by whatever it is and u by whatever it is, and then it will do the simplification. Do it now. I mean, let's spend a few minutes. Just do it. Do the replacement now. If you know what the replacement actually is, let me look for it. Weak interactions. No, it was in an additional sheet that I had. Bhava scattering, Moeller, Rosenbluth, two diagrams, Moeller scattering, electron non-relativistic. Of course, I have everything except the problem that I want to do. So I don't have the replacement for E mu. The problem is that these are unequal masses. So you have to be very careful with the replacement for cosine theta. Okay, you can do it in piece, and then we can compare next time whether it agrees or not. Okay. Okay. So somebody else wants to describe the next process? Abhishek, you want to take up the next one? Oh, this is the only one you had. Anybody else? Any other process? You have Rosenbluth? You've done it. Okay, then let's have a look. Yeah. So you explain to us what it is that you've done.
Here I was used crossing, and I gave only one diagram.
But why did you have to use crossing symmetry? It's the same kinematics, no, as E mu to E mu. You don't have to cross.
E mu was E minus mu minus V, and Rosenbluth is E minus mu plus to E minus mu plus.
Yeah, okay, fine. But it's still the same process, you know, and there's only a photon exchange and nothing else. Yeah. So it doesn't matter. You have to see whether it is E minus mu minus or E minus mu plus, also the same, because there's only one vertex. Okay. And because of lepton number violation, you do not get any other diagram. Similarly here, because of baryon number conservation, there's only one diagram, so you don't even have to call it crossing, except that mu minus has gone to P plus. Okay, fine. It is
basically the same thing as LTO.
Okay. Then what did you do?
So I replace these momenta.
Yeah. Okay, fine. Yeah.
Then I compared the differences that it was giving these two correctly.
So this is actually not Rosenbluth. In and a point like Dirac proton, which in reality is not point like. So the Rosenbluth formula is to replace the vertex at the proton end by a more complicated structure. Okay, so that's the thing that I had written on the blackboard the other day. So you have to introduce with the F1 and the F2 the form factors, and then you have to go through it and get the corresponding answer with that. So that is Rosenbluth. Okay, and that is what you people need to do, so that you get a hang of what Rosenbluth formula looks like. You've done it? Yeah, that's fine. You can do that too. But if you have something as powerful as fine calc, you should try to use the inbuilt functions. Of course, there is nothing here that we cannot do by hand. What fine calc can do in 10 seconds, it will take us something like 6 hours to do. Okay. So the whole point of introducing you all to fine calc in this class is you can immediately start to get results. Okay. Because in a sense, all these topics are supposed to be a prerequisite for this course, that you have already done it in particle physics, you've done it in field theory, whatever. But I know that when people do things in courses, at that time you do it and it evaporates immediately after the final exam. So we want it to recondense in your brains using fine calc and so on. Okay, so that's the point of this. Anybody else? Yeah. Hmm. Yes. Yeah. Yes, sure, I agree. Then you get the Rutherford formula. Yeah. So these are the stages that I was talking about. In the limit of an infinitely massive proton, you get Rutherford formula where you also neglect the spin of the electron. Okay. Then if you introduce the spin of the electron, then there is a correction to that which gives you the Mott formula. Then you ramp up the energy some more, and then probably it starts to probe the structure of the proton and starts to see the spin of the proton. So for Rutherford, you're treating both the proton as well as the electron as spinless. Okay, because in the really non-relativistic limit, nothing happens to the spin. The spin doesn't flip, it doesn't interact, nothing. Okay, then the incoming electron, if it goes around the proton like this and does scattering, then there's a kind of a magnetic term associated with the Dirac properties of the electron. Then there's the interaction of the spin of the proton with the spin of the electron. So it's as if it is behaving in a Dirac-like way, but it's not correct because all the predictions from there are wrong. Then you have to introduce form factors for this, and then that gives you the Rosenblatt formula. And in low energy limit of the Rosenblatt formula, it will give you the correct magnetic moment of the proton, which is this factor 2.78 or something like this. Okay, while for the neutron it is minus 1.91. So if you take the full Rosenblatt formula and look at various limits, you will start getting each one of these. Okay, so that's the way to look at it. Anybody else has anything else to present for the moment? You guys have better start participating, otherwise there's no point. It will be just like any other class and course. Okay, fine. So let me now start my own lecture if you people are ready for it. So yeah, so we can start where we left off, and if one of you can remind me where we were in the previous class. I think it was the muon muon decay. That's what we had done, and from there we had also got the tau lifetime. We had looked at the fifth power dependence of the width with respect to the mass, and then we had to account for the various allowed final states of the tau, and then we got the answer, which is reasonably good. Can somebody remind me what that answer was? Let's again try to recall. What's the lifetime of a muon? Lifetime of a muon. Yeah, that's of course in the rest frame of the muon, and that's the reason why it is such an important particle, because the longest lived elementary particle that is unstable, of course. And then we saw that the lifetime of the tau is 2.9 times 10 to the minus 13 seconds. So that's 7 orders of magnitude lower, because it is so massive. Okay, it really is extremely massive, thousands of times as heavy as the muon, and therefore, just from the principles of quantum mechanics, it is going to simply decay very fast. Now let's see. Supposing you want to do the same thing now for the neutron. So let's think about the decay of the neutron. Bad chalk piece. Even worse. Decay of the neutron. So at the quark level, what do you have? You have the conversion of a D into a U with the emission of a W, and you have electron with neutrino, and then of course you have two other quarks which are spectators, D goes to D, U goes to U. Of course, you are going to ask me, how do I know it is not this D? How do I know it is this D? Of course, we don't know. This is all suitably symmetrized inside the neutron. Okay, so that kind of thing, the wave function is suitably. So the role of these, you can think of these as basically spectator quarks, but not really, because every quark is continuously emitting gluons and so on. So this W over here doesn't really, it has to penetrate through this gas of virtual U's and D's and so on, and then there's a decay process that's going on. Okay, so we cannot say that it's a point like. So there are many complications over here. So the complications over here is that the D quark is always dressed not just by gluons, but by virtual U and D and S quark pairs and so on that are continuously jumping in and out of the vacuum on the one hand. But we know that even at the level of the point-like interaction, there is a cosine of the Cabibbo angle. So there are many corrections due to this. But for the moment, if you assume that it's a Dirac-like photon neutron, and we simply want to say that it's something that looks like very similar to the muon decay, then the width of this turns out to be 1 by 4 pi cubed h bar GW by 2 MW C squared times ME C squared to the fifth power, like this. This doesn't look anything like the muon result, because what you're seeing here is the mass of the electron. Okay, it's not the mass of the neutron, mass of the electron times E, this 9a squared minus 8 square root of a squared minus 1, that's a times log a plus square root of a squared minus 1. So this is the final answer, which of course is not possible for us to evaluate this. This comes from the phase space integral. Now remember that the width always has square of the matrix element times the phase space. In the case of the muon, it was one extreme where the muon is so much more massive than all the daughters that you could basically pretend that all the daughters are massless and then do the phase space integral, which is why you got that beautiful geometric result of the fifth power of the muon mass. Okay, because that's what the phase space integral turns into. Here it's the other way, in the sense that the parent, which is the neutron, and the proton are almost the same mass, so the allowed phase space is very small. Okay, and this A over here is the parameter that fixes the difference Mn minus Mp divided by Me, and this is equal to, this is something that every one of you should remember, because it shows up everywhere. It shows up in astrophysics, it shows up in, you know, neutron lifetime, etc., etc. This 782 keV is the energy that is available for the electron. It's the maximum end point of the electron spectrum. It's the end point of the electron spectrum, defined by, divided by 511. Yeah. Yeah. None of them is kinematically allowed. If the only energy is 782 keV, right? Whereas the mass of the muon is a little more than 1000 keV, so it's not allowed. So why, nobody knows. Why is it that the world is this way? Why is it that the neutron can only decay? But in principle, it could also emit a photon from the electron leg, for instance. Okay, so you can always have that kind of a process, but it is down by a factor of alpha, right? Because there will be an electric charge of E, the square of the matrix element. So you can always have radiative processes where there's a photon in the final state, two photons in the final state, any number of photons in the final state, subject to momentum conservation. Very soft photons you can have, carrying fractions, but the probability of such events is very small. And what you can do is you can have a correction to this and lump all those soft photon contributions into some function which is the sum of all such processes. But I don't think for the neutron even this thing is important or necessary or anything like that. But you will all be surprised to know that even today the mass of the neutron is not that well known. It is very difficult to do a precise measurement of the mass of the neutron. And let me ask you why. You people can think about it for 2 seconds and tell me why you think it is very difficult to measure the mass of the neutron. Of course, you may say it's unstable, so it's difficult to measure it, okay? But then that's one of the reasons, okay? The other reason is, where is the source of neutrons? You have a source for neutrons? Do you think you can find a source for neutrons? Yeah. So these are called reactor neutrons. So neutrons that are produced in, let us say, Kalpakam or in Tarapur and so on, those are neutrons with which you can try to do some experiments. Okay. But there's a problem with these. What is the problem with this? Forget about all that. There's a fundamental property of the neutrons that you produce in such reactions, which would be a problem. They have some energy, not necessarily high. They are what are called thermal neutrons. Okay. So if the neutrons themselves have motion, and as you said, you can't trap them in magnetic fields and so on, so you have to find a bottle in which you have to keep these neutrons and try to measure their masses. Okay. So neutrons come in many varieties. Who got this low energy precision experiments? So you will have to study this and see what are the best limits on the neutron mass and what they are going to do. But they also do some very interesting experiments with such neutrons. They have an effective potential for the gravitational field itself. Okay. So there's an effective theory for the gravitational field in which you take neutrons and then you study the quantization of the effective gravitational potential with neutrons and try to study their. So these are experiments which are done in Grenoble in France, which has dedicated reactors for scientific purposes, not for energy purposes. So in Grenoble they do these experiments. So neutrons come in various varieties. They are called thermal. Some of them are cold. And what comes after cold? Cold. It's ultra cold. So these experiments are done with ultra cold neutrons. Okay. And in fact, you can study gravitational potential. And this is linked to the mass measurements of the neutron. Mass measurements of the neutron. Grenoble is a place in France which has a research station. So here they have research facility for neutrons. They actually have a reactor, I'm told, which is for scientific purposes. It's also the European synchrotron facility. It's the science city of France. Besides Paris is the other one, European synchrotron facility. I don't think so. I think it's just a non-relativistic potential that they have, and they want to look at the energy levels of this potential. It's very interesting, worth reading. So our friend Mr. Kanishka is going. Kanishka, you're the one who's going to tell us about this. Okay. So if you have the number of electrons versus the energy in a sample of neutrons that are produced, it'll look like this, and it ends at 782 keV. Okay. Okay, now you people can take out your Mathematica and plug in this formula and give me the answer for this, for the various parameters. Now somebody has to remind me. See, this is a class on standard model. So I will keep on asking you what are the values of the standard model parameters until you people memorize it. Not allow you out of this course until you tell me. GW, the other day we had it. Anybody? 0.653. Okay, then let's see. Mass of the W, 80.4 GeV. Now you plug in everything in terms of this. Now this is dimensionless, so we don't have to worry about this. So this mass of the electron, 0.511 times 10 to the minus 3 GeV. Let's keep everything in GeV units for the moment. And we need H bar to finally convert this into an answer that we want. 10 to the minus 25 GeV second. So you can use this formula with H bar equals C equal to 1, which is natural units. Get your answer and then finally divide it by H bar so that you get gamma in 1 by second. Okay, please do it. Take out your Mathematica and do it, or a calculator. Otherwise you can't do it on your calculator. And let me try to remember names again over here. So Kirana, no, you don't tell me. It's a memory test. But Aniruddha, okay, you I know. Okay, most of these guys I know. Your name I still don't know. Devendra. Shubhadeep, okay, good. Sudhir, okay. You're of course not taking, you're the only ones not taking it for credit. Everybody else here seems to be, right? Everybody here? You're auditing it, okay, because you finished your comprehensive and all. Okay, fine. But you're allowed to audit so that it shows up in your transcript. Okay, please. This is a course as much in Mathematica as it is in standard model, right? Possible, yes, thank you. But since we put H bar equals C equals 1, we are okay. You have Mathematica on your laptop, you should get, yeah. But it's there on the system, okay. For Leo, this should be very simple. You have Mathematica on your cell phone? Yeah. Good. But I'm just making sure everybody gets a hang of these numbers. Otherwise, I can just keep on writing. There's no point. Yeah, but you have to divide it by this, no? Still doesn't sound right to me. So it's not right. So because tau is supposed to be 1318 from this. Ah, did anybody get it so far? Actually, after this, I want tau. Tau is what I know, and and you should get a number that is how many roughly? What do you expect it should be? Of that order, let's say of the order of 1,000 seconds. Order of 1,000 seconds. Of course, there'll be some corrections to all this, but this had better come out right. At least the order of magnitude should come out right. Doing it on Mathematica. Okay. So you get an answer in natural units. Then you want to convert it to inverse second. In order to do that, you have to divide it by h bar. Otherwise, you get gamma in natural units. No, no, no. This is the reason why I've given you this problem. When you compute something like this in natural units, put h bar equals c equals 1. Okay? Then you get an answer for something in natural units where there is no dimension at all. Okay? Then you want to convert it to a dimensionful quantity. And then you have to look for what units have survived, and then you have to multiply it or divide it by either h bar or h bar c or c, so on. Okay, when you compute this particular quantity, there is nothing over here. Okay, this is the fifth power, this is the fourth power. Okay, okay, then what do you need? I did this calculation the other day, so but now I don't remember it anymore. Okay, fine. So you people have got an idea of how to do this. So you're saying it's not h bar? No, it is. It is. See, let's look at this thing. This thing has GeV to the fifth power. This GeV to the fourth power. Okay. So the final answer over here in natural units, you will get gamma in GeV. Okay, that's no good. So you have to divide it by h bar, which is GeV second, so that the answer that you get is 1 by second. Okay, so I'm right. So somebody confused me here thoroughly, but it's okay. Now you agree or not? Do this calculation with h bar equals c equals 1. Okay, all dimensionful quantities are now only carrying GeV units, nothing else. GeV to the fifth power, GeV to the fourth power. What survives in this expression is GeV, but you want gamma in terms of inverse second. So you have to take this answer that you got in GeV and divide it by h bar, which is in GeV second. So the GeV cancels out and you get 1 by second. Yes? Oh, you mean to say that my answer is wrong? Oh, sorry, this is to the fourth power. Thank you. Thank you. Yeah. Good, good, good. You should keep questioning. Okay. This is also obvious, no? If you have mw square in the propagator, then in the amplitude you should get a fourth power. Today's class is more in the spirit of a tutorial, okay, but that's okay. I consider this to be a 2:1 course. You know what 2:1 means, of course, in your system, right? You are getting 1318. You are my pal. So this is 1318. 1318 seconds. What did you get for this? Times? Come on, then how can you? Gamma. Second to the -1, right? Okay, so this is the answer, but this is too big. Okay, so what is the problem? What is the change that we need to make over here? So this has to do with all the properties that I mentioned over here, that the factor that you assume of 1 minus gamma 5 is not correct at the quark level. So let us replace this by something else. What would you like me to replace this with? So in the notation that I have, so this is to be replaced by CV minus CA gamma 5. And what do these two symbols stand for? CV and CA, what are the names of these? This is the vector coupling and this is the axial vector coupling. Okay, so it turns out that we need some independent measurements of these things, and then it turns out that CV is equal to 1. It's very unbelievable, but CV is equal to 1, and CA is a number that's close to 1 but not quite, and not so well determined. There is some uncertainty to this. Now this is a pretty remarkable thing, that the CV is still equal to 1. Okay, it more or less remains unchanged. So this is an amazing property of the weak interactions, despite the presence of the strong interactions and all the dressing of this quark surrounded by the sea of quarks and antiquarks and so on, that it still stays the same. And this was explained by Feynman and Gell-Mann. It's probably their only joint paper, and this is called the conserved vector current hypothesis. Vector current hypothesis. How about this? This is not conserved, no? But it's still close. It's still close to 1. So let's give it a name. What name would you like to give it? It's not fully conserved, and therefore you can call it partially conserved. So this is called partially conserved axial current hypothesis. So this is called the CVC hypothesis, and this is called the PCAC hypothesis. Okay. So then this is going to modify the lifetime, and it changes the lifetime in the following way. So there is a factor now that will change this, and the lifetime gets divided by 1/4 CV squared plus 3A squared. Now somebody compute this for me for the central value here. Please give me the number. .46. So the lifetime goes from 1318 to 1.46. So you can give me the answer again. 902 seconds. Okay, so this was for all the dressing over here, this dressing effects. That's what leads to that CV and CA. But there's still this cosine theta. So let us now divide this by cosine squared theta C. Somebody give me the answer. Please look up cosine squared theta C and then give me the answer. What does C? C stands for? Kabibo. Yeah. So please look up cosine squared theta C anywhere you want, Google it, and then give me the answer. Yeah. So when you do this, it's a 3% correction roughly, right? About 930 seconds. Now this is actually the lifetime of the neutron is about 877 seconds. Okay. So these are all like simple considerations which give you this, but we still more or less get the right answer from this. That's how it is. Life is like that. Because there are other sources also for Kabibo. It's a complicated calculation. You have to do the full Dirac algebra of introducing it over here, calculate the traces and all those things. I'm going to give you a problem now after we do the next thing that we want to do, which is pion decay. Yeah. Yes, it has to do with the fact that there are quark masses. Because there are quark masses, the axial vector is not just spontaneously broken, but it's also explicitly broken. That's the reason why the pions are not exactly massless. If there was no explicit symmetry breaking term in the QCD Hamiltonian, then the pions and kaons and all would have been exactly massless. But because there is an explicit mass term, it disturbs the axial symmetry of the QCD Hamiltonian. So these come from arguments of symmetry of the QCD Hamiltonian, and these are only approximate symmetries. They are fairly good, but they are approximate. But it's not just qualitatively convincing ourselves that these symmetries are there and they are good or not good. They are very precise. We can very precisely make and estimate the effects of this kind of symmetry breaking. There are other relations also. There's a famous Goldberger-Triemann relation also, which is associated with this partially conserved axial symmetry, PCAC, axial, partially conserved axial conservation, whole lot of low energy dynamics are explained by these things. Goldberger-Triemann relation is one of them. Then there are other relations between pion decay, pion coupling constant, pion nucleon interaction. There's I have to try to remember. There's a Miyazawa, Omer. There's a third author also, Miyazawa, Omer, and I've forgotten it. Can you just Google it quickly? Miyazawa, Omer, and somebody else relation also. There's Goldberger-Triemann. There are all these low energy results associated with these things. Who's the third person? Miyazawa, Omer, and there's a third one. Also Goldberger. Then there are other sum rules, low energy sum rules. There's an Adler-Weisberger sum rule. There's an Adler sum rule also. All these are all the guys who studied all these effects of symmetries. See, you have to go back at a time when people didn't know the underlying dynamics. These are all based on ideas of symmetries that the strong interaction Hamiltonian could have. Okay, no quarks and leptons were known, no quarks and gluons were known at that time. We are talking about 1960s. So just from symmetry principles and trying to relate many different phenomena, they were able to figure out a lot of very important stuff. Okay? All this has to do with the problem of trying to understand the dynamics of the strong interactions at low energies where you have no perturbation theory in any coupling constant except in effective theories. The other day, Mr. Kanishka was asking me how come we don't write down all these color indices and so on while we are spending so much time talking about the weak interactions. We are doing QED and we are doing electroweak interactions in perturbation theory in Feynman diagram language because we can do it, because the particles in the asymptotic states are the same as the degrees of freedom that participate at the level of the Lagrangian, electrons, leptons, neutrons. Whereas when it comes to the strong interactions, the degrees of freedoms are quarks and gluons, whereas what you see in the low energy spectrum are protons, neutrons, which are all bound states. Okay? So in some way, it is almost useless to do perturbation theory in alpha S at low energies. You can do it at very high energies in some limits, such as the deep inelastic limit. There you can do perturbative quantum chromodynamics, but you can't do it in the low energy spectrum. Okay? So when you say neutron, it means that the quarks and gluonic degrees of freedom have frozen out, and what you have is something effective like protons and neutrons. When you're describing the properties of water, let's say dielectric constant of water, you don't do it at the molecular level, right? You say that I have a glass of water, although I know it has an Avogadro number of molecules. I'm not going to do microscopic theory, but I'm going to study its property in the form in which it manifests itself, namely the water that is in my bottle. And what are the properties that I can study of water? It's a dielectric constant. Or I know that it undergoes phase transitions. It can become ice or it can become steam. So you study it thermodynamically. You can study certain extensive properties of water, okay? But you don't need to do it at the molecular level. Of course, you may have a different context where you may have the motion of 20 water molecules through some nano wire or something like this. In that case, you have to do it with water molecules. So it depends on the phenomenon that you're looking at, okay? So many of the phenomena that we look at, such as neutron decay, is where the quarks are not behaving as quarks, that they are frozen out and it has formed a bound state. Still, I'm trying to guide you through this book of Griffiths. There are a couple of chapters, sections where we do talk about the color degrees of freedom, and I will do them also. Okay? The idea is by, let's say, end of next week, we have gone through virtually all the chapters in Griffiths, and every one of you can pick up Griffiths after a cricket match and then open this and you can follow what is going on, except some of the last chapters which requires more discussion. Okay, now what is it that I want to do? I want to do the decay of the pion. Okay, decay of the pion. This is one of the simplest, and here we know that pion comes in, produces a W like this, and then produces a lepton and a neutrino like this, and we can write down the matrix element as GW squared by 8 MW C squared U bar 3 gamma mu 1 minus gamma 5 V 2 times F mu, where F mu actually is something that represents the pion which couples to the W. Okay, so in principle this should be a form factor, but in practice it is not a form factor, and I want you to tell me why. In principle this should be some f of q squared, okay, where q is a momentum that is carried by this, but here in this case you don't need, you just introduce it as a constant. Why? Because it's only a two body decay and the energy is fixed, and you don't have the possibility of q squared varying, it is fixed by momentum conservation, so you merely call it F mu, right? And I'm going to tell you without proof that gamma is going to be, where I'm going to call this F mu as some constant F pi times P mu. F pi squared by pi h bar and pi cubed GW by 4 and W to the fourth power times ML squared times M pi squared minus ML squared squared. P is the momentum of the pion. Yeah. Later you can go to the rest frame and all, it doesn't matter. But for the moment it is S P mu. Yes. Yeah. You tell me. You tell me. Think a bit. There is no other vector you have in hand. Okay. When it came to the Dirac particle, it has a gamma mu which transforms as a 4 vector, right? So you can put a gamma mu, point-like interaction, gamma mu, fine. Okay. If it also had some structure, then you could have put in a sigma mu nu, p mu, etc. Whereas for this hadronic part, this is already a vector. We know that the weak interactions have the form of v minus a. Okay, that's what it's this. So if you want a Lorentz invariant quantity and you have something that's transforming with a Lorentz vector index, never mind the 1 minus gamma 5, and it has to be contracted with some other vector because this thing has to be Lorentz invariant. What's the only vector you have in hand? There's no other vector. But as Ranjani was asking me before this course, supposing the pion had had a spin, then it would have had a spin vector S mu also, then in principle you could have had that. But because the pion is spinless, it's like this. So you see, even when you write down a small line like this, there's a lot of physical input that has gone into writing down a structure like this. Okay. Can somebody evaluate this trace for me and tell me what it is? Because I want to turn this into a trick question for you all. Every one of you has Mathematica. Somewhere you have Mathematica. You know how to use it. You learn. You ask your friends to teach you. Okay. I'm too old, but you ask some other people in your lab to teach you. You have to take the spin and so on of this particular thing. Yeah, of course. Yeah. Please do it. I think Chaitanya knows how to do it. I want you to take this part of it and then square it and take the trace, obviously, because we want it in the m squared. Okay. I want you to take this part of it, square it and trace it. And I'm going to ask you why I'm asking you to do this. Mr. AAGB, you don't have? No Mathematica? You don't have charging? Why? The battery is gone. You guys should replace your batteries or replace your laptop. No Mathematica? Not here, not anywhere? But you have Mathematica access. Okay. Take the simplest possible. You cut it from your emu to emu notebook, take it out, create a new notebook, and square it with FineCalc, and let's see. Huh? No. Then one of the other guys will do it. Yeah, Abhishek, take this, cut and paste it into a notebook, and then do it. This reminds me of a story. There's a guy a couple of years a little older than me in IIT. So one day he was smoking a cigarette. So one of his teachers said, "Young man, do you know that smoking is a slow poison?" So he said, "Yes, and I'm in no hurry." So it's like that. I'm in no hurry. Because unless you people learn to do these things, there's no point in my life. Mathematica is a slow poison, I guess. Yes. It's very important that you give a mass also. Okay. And the neutrino is massless. Yeah, we corrected it. Yeah. Here, this is only the matrix element. There it was a square of the matrix element. I don't know actually. So it was only the final answer there where we had grouped all the terms and cancelled out. Okay, like this you mean? Okay, you must be right. But anyway, yeah, I guess so. I always keep h bar equals c equals 1, so it doesn't matter. Only at the end I make sure. Mr. Kirana, you have? You're still installing. Okay, see, it's a good thing that we are doing this in class. I'm forcing all of you to do it. But why am I asking you to do this? Of course, I may be insane. That is also one possibility. But what's the other possibility? The other possibility is I want you, after you have done this, to change this to CV minus gamma 5 CA so that we can explicitly see the role of the CV and CA in the final answer. Okay, that's the reason. P2. What are P2 and P3? P2 and P3. Okay. So then we have to be able to convert it into this, right? Into the mass of the muon, right? See here in this particular problem, where you do the two-body kinematics, in the rest frame of the pion, there's only one quantity, which is the mass of the pion. And after the decay, the only other quantity that you have is the mass of the lepton, because you've thrown away the mass of the neutrino. It's massless. So whatever it is that you do over here with P2 and P3, etc., the final answer should depend only on the masses. Okay. So what was the two-body kinematics that we were supposed to have done long ago? I think we did it, no? Didn't we do the two-body kinematics? Okay, not here. Okay, here's the two body kinematics. Pi goes to mu plus nu mu. Then P mu is m pi squared minus m mu squared by 2 m pi times C is mod P nu. P mu is, this is a problem we always give to students in the Viva, right? 2 m pi C squared. And E nu is equal to P nu C. And the velocity is equal to P C squared by E. And V of the muon is m pi squared minus m mu squared m pi squared plus m mu squared C. So you said what P2 dot P3, right? So you know what each one of them is. You know the energy, you know the momentum, this. So you can get P2 dot P3 from this. Please get it. And more importantly, get the answer after you put the CV minus gamma 5 CA. That thing will give you a P mu, which is m squared, okay, for the muon. Yeah.
And then the gamma mu and gamma nu will get.
Yes.
And then when you contract it with that, you get a x dot.
Yes.
That will also be.
My point here is actually to look more at the dependence on the CV and CA, okay? So this is being given as an exercise to you all. People who have already done N courses in particle physics and field theory is to do the decay of the pion completely. So don't ask me, you tell me, okay? You find out the answer and you tell me. Because I am an old man and I neither remember it nor do I need to remember it, right? Nobody is going to ask me anything ever again. So whether I know or I don't know, it doesn't matter. You have to know. Okay. 16 CV squared. Okay. P2 dot P3 then. That's it. I can't believe it. It's impossible. It must have a CV and CA dependence separately. You see this particular answer that you have, where it depends on the mass of the lepton, okay, like this, is what is responsible for what is called helicity suppression, okay. You would look at this and you would think that it's more probable that the pion decays into an electron rather than into a muon because of the allowed phase space. This is the phase space, which is the m pi squared minus ml squared, okay. This for the muon is rather small, whereas for the electron this is large because this can be thrown away. But it's this term which is telling you that the neutrino is left-handed, okay, and that is why the muon mode is favored over the electron mode because of the V minus A nature of the pion, V minus A nature of the weak interaction. Okay. So this is a homework problem for you all to do the pion decay completely from scratch. Use any book you want, use Mathematica, use anything you like, discuss amongst each other, all of you together or in any group, and come back and tell me the answer for the most general form when you have CV and CA, okay? Right? Leo, you agree with me, right, that this is the helicity suppression thing. It's because the ml squared is showing up over here that the electron is suppressed over here, okay, and the muon is more pronounced because of this particular thing, and that's the key to understanding why the weak interactions have a V minus A. And the reason why it has a V minus A is because the W couples only to left-handed neutrinos. This is fundamental when you're talking about the standard model and parity violation. This is the fundamental property, that the left-handed particles are treated differently from right-handed particles. So obviously we will need more practice with fine calc, fine rules. Keep doing all these things until you get the answer. Okay. It's also worked out in Griffiths. You can have a look in Griffiths and see, put in CV, CA explicitly. Yeah, that's, yeah, yes. Hmm? I don't know, maybe maybe we have to do this and see what is happening. Okay. Yeah, I'll have a look also. This is something that I just gave you on the spur of the moment. I didn't think about it, and I didn't think that I'd run into all these difficulties, but it's a good exercise to work on. No, this is the standard 1 minus gamma. CV equals CA equals 1. Okay. Yeah. I'll also have a look. I mean, I shouldn't have asked a question without myself knowing the answer. But I just thought that since you people are smarter than me, maybe you will get the answer before me. Could be electron or muon. Pion is heavier than both the muon and the electron. No? So that is why it has two modes. It can decay into the muon, and it can also decay into the electron. It can also decay into pi 0, because 139, 135, there's a 4 MeV which is allowed, so which can go into an electron, because electron is only half an MeV, right? That's also an allowed mode, pi plus going to pi 0, electron and an antineutrino, and that's called pion beta decay, and that's the process that you have got. Okay, that there are experiments which study these things at high precision. Which one? Yes. It's then a 3-body decay. If it is pi plus going to a pi 0 plus positron and neutrino, it's a 3-body decay. So it is analogous to the neutron beta decay. Okay, and it's very interesting that it has only a vector-like coupling. There's no axial vector coupling there, because this thing is a pseudoscalar. So that again confirms the CVC hypothesis in a very nice way. Okay? Whereas the neutron has both CV and CA. For the what do you call it? For the pion, there's only a CV. So these are all the old processes of hadronic physics which test the standard model in a very interesting and important way. Okay, so this is a problem that all of you have to work out and get back to me. I find it impossible that this is just, to understand it, this is just. Any other questions? Obviously. We are talking about a theoretical world in which CV and CA may not be equal to 1. We know for a Z boson, CV and CA are not equal to 1, right? They are mixtures of various things. So, CV equals CA equals 1 is what is called maximal parity violation. Okay, so maximal parity violation means that the neutrino is always left-handed. If it was less than maximal parity violation, then you can have an admixture of left and right. That's the point. Yes. So today we have the standard model where it is all inbuilt into the standard model. At a time when standard model was not known, people were grappling with all possibilities. They grappled with tensor-like coupling, scalar, pseudoscalar. So if you look at any book like Bjorken and Drell, which is one of the older books, you will see that they list all possibilities: scalar, pseudoscalar, vector, axial vector, and tensor. Okay. So V minus A form, Sudarshan and Shack and Feynman-Gellman, they gave this hypothesis to explain parity violation. But parity will not be violated if you have only V or only A. It must have both V and A. Okay? But the question is whether it is equal, whether CV is equal to CA has to be established experimentally. Okay? So there are all this, somebody here has got electroweak precision tests. So you guys will try to figure out how it is that we have established CV equals CA equals 1 and so on and so on. No. It's just a name that I have given over. We know now with the standard model that they are both equal to 1. And I am trying to say that if CV equals CA equals 1, then you get those dependence of ML squared. Okay? And I am asking you, supposing you didn't know, you went back to 1955 and you put in CV equals CA, I am asking you what is the dependence of the lepton mass, okay, so that you can understand why it is that it has to go as ml squared. And the reason is this: if you have a particle that is spinless, oh gosh, next time, okay, we're already extreme, you have to go for your next class, I suppose, okay.